All right, let's begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students again. Just pray to be with us today. Help us to just understand what we need to about topology and complex plane and complex differentiability. We just thank you, Lord, that you've given us minds that we can understand your creation with. We thank you and we glorify you for that, Lord. In your name I pray. Amen. Okay, so last time we talked about sequential limits, but I want to just talk a little bit more about topology, which topology, in short, is the study of continuity in the abstract. Or you could also say it's the study of open sets. I mean, what does it mean for a set to be open? All right. But we gave this definition for limit last time. The limit, as z goes to, say, z naught, of f of z being a complex function of a complex variable, is equal to L if and only if for each epsilon greater than 0, there exists some delta greater than 0, such that 0 less than modulus of z minus z naught less than delta implies that the modulus of f of z minus L is less than epsilon. So this is pretty much word for word the definition of limit we gave you in Calculus 1 here. Simply the absolute value has been replaced by the modulus. And so, of course, this is a little bit different than the sequential limit we talked about last time, which was, of course, done in terms of looking at the tail of a sequence. Here we're looking at limit points points closer and closer to z naught and studying what happens with those. Now, so that's your definition. From this definition, you can prove the usual limit laws hold. All right. So what are the limit laws? The limit as z goes to z naught of f of z plus g of z is what? Right. Now this supposes what about the limits on the right-hand side of this equation? I'm supposing, of course, that the limit of f and the limit of g separately exist. If that's not true, then I can't use this limit law, obviously. Listen, the reason this is true, the reason this limit law is true, basically follows from the following inequality. If you look at the modulus, let's say that this thing's value is L sub f. Let's say that the value of this guy is L sub g. Let me show you why this limit law is true. It's essentially following from this simple inequality right here. The modulus of f of z plus g of z minus L sub f plus L sub g, right, is less than or equal to, well, the modulus of f of z minus L sub f plus the modulus of g of z minus L sub g. This is the triangle inequality for the modulus. And so if the limit of f and the limit of g separately exist, what does that say? That says that you can make the quantities on the right-hand side of the inequality I just wrote as small as you like by choosing epsilon, right, like you like. So essentially what you do is just force this to be epsilon over 2, force that to be epsilon over 2, choose a delta, which is such that both of those conditions are imposed as you can, and then that gives you that the sum of f of z plus g of z is less than the sum of the limits, which then shows that the limit of the sum exists and is just the sum of the limits. The details are they're not in the notes. I tell you to go back and look at my Calc 1 notes if you want. The proof is the same as I gave in Calculus 1. But anyway, if you want me to show you the details of that proof, I'm happy to show you in office hours. Another limit law is as follows. The limit as z goes to z naught of f of z times g of z is equal to the limit of z goes to z naught f of z times the limit as z goes to z naught of g of z. So the limit of a product is the product of the limits. Again, supposing that the limits on the right-hand side exist, that's still true. What's the other limit law we like to use? Basic one. How about the limit of a quotient? When does this limit exist? I'm starting to really wish I just wrote lim everywhere. I'm writing lim as z goes to z naught. So much writing. That's true only if both limits exist and what? Right, assuming the limit of g is not equal to 0. Very good. So those are your limit laws, and you can prove those in essentially the same way that you did in Calculus 1, replacing absolute values with modulus. Now, of course, I can also do what? I can also pull a constant out. If that's a complex constant, I can pull it out, right? So, but that would put a c here, and there would be a c here as well, for what it's worth. And a c here, and a c here. Oh man, so many c's. Did you get that? Okay. All right, so those are your limit laws. You say, okay, well, what's the connection between these limits and the sequential limits we said last time? Well, here's the relation. Little theorem. The limit as z goes to z naught of f of z is equal to L if and only if for every sequence Zn converging to Z naught, we have f of Zn converging to f of Z naught. So there's this connection between the epsilon delta limit and the sequential limits, all right? I have the proof of one of these implications in the notes. I'll let you look at it. I have a link to show you the other direction, which is by contradiction. So, but that is also, sometimes it's easier to think about a limit in terms of sequences than the epsilon delta. You'll get more into this when you take real analysis here, okay? So I'm going to go back to the topology now. That's what I had to say about limits. I would say that the epsilon delta definition is really the topological definition of the limit, because if you parse what this is really saying, it's saying that the inverse image of open disks in the range is an open disk in the domain. So the inverse image of open sets is open is essentially what this limit is saying. You might not see it like that, but if you flesh it out, it's actually the case. And so that definition that the inverse image of open sets is open is the abstract definition of continuity in more arbitrary topological spaces. All right, well, yeah. We could spend a whole lecture on the little bit I just told you right there, all right? But that would kind of be a digression. Okay, so we need to set some terms here. So we talked about open set before. What was open set? Basically means it could be something like this, right? Maybe all of this is, both of these together are some set U, right? This would be an example of an open set because no matter what point you pick inside the dotted lines, see, times like this I really wish I had a chalkboard because it's really hard to shade. But I'm talking about all of this being the open set, okay? I'm saying it's an open set because if you pick any point, you can find an open disk around the point centered, inside there, right? So this is an open set, but this would not be what's called a domain. What's a domain? A domain is a word which we use with a technical meaning in this course, all right? Now, in other parts of math, it's not necessarily the case, but here it's the custom of complex analysis to use the word domain for, oh goodness gracious, I'm trying to, where did I put that stupid definition? This is actually definition 2.1.26. I'm not quite following the order of my notes. I hope that's okay with you guys. But a domain is an open connected set. So that begs the question, It's open and connected. It begs the question, what does connected mean, right? Well, it means you can't separate the set into pieces, which are disjoint, right? So this is the example I have above is not a domain because it's been disconnected, right? So that's, you can't find I found a separation. It's separated into, let's say this is U1, this is U2. I have U is equal to the union of U1 and U2, right? But U1 intersect U2 is the empty set. So that's a separation, all right? It's a separation of the set. So connected sets don't allow for a separation, but that's kind of, well, that's very set theoretic. Like we want to think more geometrically in here. So what's another way we could capture the notion of a set being connected? Well, the definition which is given in Gamelin is basically that if it's connected, then if you take any 2 points in the set, you can get from one point to the other by a broken line segment, although that's just a line segment. So, but on the other hand, if I try to go from here to here, you see I can't get from U1 to U2 without going outside, right? So the definition of connected set is as follows. But before I give you the definition, I have to define what's a broken line segment. Broken. Well, if you call it broken line segment, I'm sorry, I forget the terminology here for a second. I guess he calls it a polygonal path. That's probably a better term, polygonal path. And so here's a picture of what that looks like. But it's just a finite number of line segments, put together to go from one point to another. And so, this has got, say, Z naught, here's Z1, here's Z2, and so forth, right? So the polygonal path gamma, it's something like Z naught to Z1, union Z1 to Z2, union union Zn minus 1 to Zn, where n is the nth, the end point. Remember that the notation Z naught to Z1 in here, it's the line segment from Z naught to Z1, right? Remember that? So like P to Q, it's the point set P plus T times Q minus P, such that 0 is less than or equal to T is less than or equal to 1. There's a parameterization of that point set. Which, by the way, I think is kind of funny, right? Because all of a sudden, if you write something like, 4 comma 3, all of a sudden it's not crazy anymore, right? That's just the directed line segment from 4 to 3. So there's an orientation here. So it's it's piggybacking on interval notation. It does reduce to interval notation when things are in the proper order in the proper way, right? But it's a generalization, and it's useful for us for talking about what a polygonal path is. Okay, so what's the definition of connected now that we have this notation? Exactly. So definition, U, a subset of the complexes, is connected if and only if for each pair, let's say P comma Q in U, there exists gamma, a polygonal path, which begins at P and terminates at Q. And gamma is a subset of U. And yes, it could actually be equal. I mean, you could take the stupid case that U is a polygonal path. That would be a connected set. So a domain is an open connected set. So whenever I say domain for the rest of this class, you should understand open connected set. And you're entitled to all the rights and privileges thereof.
Today or the rest of the semester?
I was speaking of class in the global sense this semester, yes. Stupid English. All right. What's a region? Basically, you take a domain, paired with some or all of its topological boundary. So let's see here. This would be a domain because I can take any 2 points, like this one and this one. Now I can't connect them with a line segment directly, but I can do this, right? And you can see from my picture that it's connected. I mean, it's obvious, right? And with the dotted lines, it's a domain, right? But suppose I were to put a hole in it, right? Then I've thrown in some of the boundary, right? So this smiley face or whatever it is, without the, with the hole deleted, it's not open because there's some points which are on the boundary, right? They're not interior points, right? Like this point right here. It's not interior, right? So that means that if I have that set, it's not open because not every point's interior. So this would be an example of a region. So the interior of a region is a domain. What's the interior of a set? It's all interior points in U. Okay, it's just what it sounds like. So the interior is automatically open. It's kind of tautological. ¿Es bueno? See? Okay. All right. I'll take it. All right. So one last topological definition. Well, I mean, 2 more, actually. So the other 2 terms I need to share with you is compact. What's a compact region? Compact. So a set is compact if it's a closed and bounded set for us. So this set would be what does bounded mean? Bounded means that you can find a disk which is larger than the set which the set's contained in, right? So everything I've drawn on the board today is compact. Bounded. Nothing I've drawn today yet is compact, though, because it has to be closed and bounded. What did closed mean? So we say V, a subset of C, is closed. That is by definition if and only if the complex numbers with V removed is open. So it's closed if the complement is open. You could restate that in terms of the boundary, I think, yeah? But, so anyway, for example, if you had this set, right? This would be compact because it's closed because it has all of its edges, right? Which means that when you delete that from the complex plane, you're left with something that goes off to infinity and it has a fuzzy edge, which means every point's interior if you think about it. And what? I can put it in a disk, so it's bounded. bounded by this disk. So compact, closed, and bounded. All right. One last term in our short tour of topology in the plane is star-shaped. Star-shaped. Now, star-shaped is a lazy man's simply connected. So something that's simply connected would be something like this. There you go. That thing is simply connected. And so a lot of the theorems that we'll state in this course for star-shaped can be improved to a simply connected domain. Or simply connected region. But the thing is, how do you define simply connected? Well, a simply connected set is one for which any loop in the set can be deformed to a point. And that's kind of technical, you know? That's kind of technical because that means, okay, so I can take any loop and I can find a family of loops inside the set which shrink down to a point no matter what loop it looks like. But how do you consider all possible loops in a set? Well, that's what you have to do to technically consider simply connected, all right? It's kind of complicated. But star-shaped is kind of what it sounds like. Here's star-shaped. So in a star-shaped set, although this might not be star-shaped, we'll see. There's got to be one point in the set called the star center. And from this star center, you can reach all other points by line segments. So I think this would be an example of a star center. Right, so I can get anywhere to there, I can get anywhere to there, I can get anywhere in here. Looks like I can get anywhere in there, anywhere in there, anywhere in there, any point in there. You can see it that every point, if I drew my star right, you can get to any point in that region by a line segment from that star center. Right. So a star-shaped region, star-shaped if all points can be reached from star center by line segment. All right? Now, star-shaped implies simply connected. But as you can see, the converse is not true, right? There are simply connected regions like this one, which don't have a star center, right? No matter where you pick it, the fact that these kind of curve around means I can't see the whole. So in a star-shaped set, it's kind of boring. Like if you only really need like one police person that just stands in the middle and they can see everything, right? Here you'd need a police force. I mean, you can't you can't monitor all parts of this thing at once from one point. You're like, I will get him a mirror. Haha. It's not allowed. Two-dimensional mirrors don't make sense. No, that's, I don't know, one-dimensional mirror, whatever. All right, so here's an example of something star-centered. How about the slit complex plane? So the usual one, right? So C minus, right, which is what? This is the complex minus what? Minus infinity to 0. What are star centers? There doesn't have to be a unique star center, right? I mean, some sets there might be, but usually there's not a unique choice of a star center. Here's what's not a star center. If I tried to use this point as a potential star center, that wouldn't work, right? So if this is my proposed star center, that definitely doesn't work because there's no way I can get like up here without going across no man's land. We're not allowed to go across the place where the set isn't, namely the negative real axis, right? So that won't work. But if you look at it, any point along the positive real axis will serve as a star center. You pick any point you like, no matter how close to the axis, you can choose a sufficiently shallow line that will just reach it. And you can explicitly find, right, you can look at the, and this is actually pretty, I mean, so what is the... All right, let me just talk about the problem of showing 1 as a star center for the slit complex plane. So to do this, we consider a line segment from 1 to some point z in the slit complex plane, and our goal, of course, is to show that this line does not cross the negative real axis in the complex plane. But, I mean, geometrically it's obvious, but here's the details. So, if you can think about the line segment, you can parameterize it using t, and so if I pick a point a plus ib in the line segment gamma, that means there has to be some time between 0 and 1 for which a plus ib is equal to 1 plus z minus 1 times t. Now if you regroup the terms here, that gives you 1 plus x minus 1 times t plus iyt. Alright, so our goal is to show that a plus ib does not lie on the negative real axis, which is to show that the curve up here does not cross that, which is geometrically obvious, but anyway, here's the proof. So if b is equal to 0, in other words, if it's on the x-axis, we really need to show that that point has to be in the positive real axis, all right? So if b is equal to 0, that means that yt is equal to 0, because a plus ib is equal to this, but imaginary parts have to match up, so yt is 0. But if yt is 0, either t is equal to 0, which means that you're at the point 1, which is clearly, you know, fine, or you're at y equals to 0. Now, if y is equal to 0, then a plus ib, okay, so t equals 0, we get a plus ib equals to 1. If y is equal to 0, then since x plus iy is an element of the slit complex plane, that means x is greater than 0. All right, but that then means that a plus ib is on the real axis when z is equal to when z is equal to 1, or gamma is a line segment from 1 to x, where x is greater than 0, which incidentally means then that if you go back to the equations up here, right, if x is greater than 0, then we can go back up here, x greater than 0, t between 0 and 1, it's easy to see that the quantity 1 plus x minus 1 times t has to be positive, right? Think about that. If x is greater than 0, then surely this quantity here is positive because t can't go beyond 1. So this quantity here can be at most, it could be minus, well anyway, just look at this here and think through it. You can see that that has to be positive, which then goes to show a plus ib is on the positive real axis. Thanks. You know, the topology or anything, we're done. There's one theorem that we might go over maybe some other day, but theorem 2.1.28 says that if h is continuously differentiable function on a domain D such that the gradient is 0 on D, then h is constant. So if you have the partial derivatives, partial h, partial x, and partial h, partial y equals to 0 on a domain, then it follows that the function's constant. So there's some connection between the topology and the calculus here. But I'm gonna move along here. I mean, that's an interesting result. It's on page 28 of my notes, but it's kind of off the beaten path for what I want to talk about for the remainder of today. And that is the definition of an analytic function. So, here we go. Definition. If the limit as z goes to z naught of f of z minus f of z naught over z minus z naught exists, then we say f is complex differentiable. So I diverged from Gamelin a little bit here because I want to develop some terminology which clarifies a few things. But anyway, so complex differentiable at z naught, and we denote that f prime of z naught is equal to that limit of that difference quotient. Furthermore, the mapping z maps to f prime of z is the complex derivative of f. So, and I insist on saying complex differentiable because there's also a notion of real differentiability which is different than this. All right? So I don't want to confuse those two, so I'm going to say complex differentiable, okay? But you should be aware when Gamelin says differentiable, he might mean complex differentiable, all right? So shall we work an example? Let's see here. How about f of z is equal to, I don't know, what do you guys want? 2z squared minus 1. So let's calculate the complex derivative of this thing. So we take the limit as z goes to z naught of f of z minus f of z naught divided by z minus z naught. What's this give us? So we have 2 z minus z naught quantity squared minus 1 minus 2 z naught squared plus 1, all divided by z minus z naught. So you FOIL that thing out. And that gives you 2z squared minus 4z z naught minus 2z naught squared. Let's see here. I mean plus 2z naught squared, rather. So, of course, these ones canceled, right? See that? These guys cancel. And then, so I've got minus 2z naught squared divided by z minus z naught. Here's where we're going to use those limit laws that I didn't prove today, but we could prove if we wanted to. It's not that big a deal. So the z naught squareds cancel, right? And you're left with what? You've got 2z times what? Yeah, z minus, I think I've... What? Where?
The very first blue line, you have on the top 2z minus z naught squared, and it's just supposed to be f of z.
Oh, I'm sorry. You know what it is? I was teaching 126 yesterday, and I've been working with the h definition of derivative. So I've got like putting x plus h in my brain, and it's stupid and wrong. So yes, thank you. Oh yeah, this is way easier than I was making it. Which is why we should use this definition for derivative. Duh. Oh man. 126. I tell you, business calculus has corrupted this lecture. Who'd have thunk it? Well, at least you guys can do it. So 2z squared minus 1 minus 2z naught squared, duh, minus, good grief. Oh, sadness. Good gracious. What on earth is wrong with me? So 2, yes, z squared. Well, let's just get to the point. It's 2z z minus z naught times what? Right? the ones canceled. You can factor, and so these cancel. And you get what? Limit z naught of 2 times z plus z naught, which works out to what? 2z naught plus z naught. By the way, here's a good exercise. Show that the limit as z goes to z naught of z is equal to z naught. I leave that as an exercise for the reader. Prove it from the epsilon delta definition. Hint, delta equals epsilon. So what do you get? 4z naught, right? So this shows you that f prime of z is equal to 4z. That's the derivative function since z naught was arbitrary. That's the mapping. Well, this is not terribly surprising, is it? So of course we could do more examples like this, but I'm going to shift gears a little bit and do something really quite different. And so what I'm going to show you is the theorem of Carathéodory. Everybody have this? I need to erase. I can erase? Okay. I mean, so this is fine, and we can basically reinvent the wheel and you know, do all those things we did in Calculus 1 in terms of the basic limit definition. You know, do all that again, right? But I think it's good for you to see another way to think about derivatives. And in fact, in retrospect, you could have done Calculus 1 this way. Only a crazy person would show these to Calculus 1, though. Carathéodory's theorem. And here's what it says. It says let f from some subset of the complexes to the complexes be a function with an element of its domain, a limit point. So what that means, a limit point, it simply means that there's lots and lots of points in the domain near that point. So you can sensibly formulate a limit. Or there's an open disk around that point. Then f is complex differentiable. Complex differentiable at A. I'll say z equals to A since it's easier to think about. If and only if there exists a function phi, which goes from D to the complexes, with the following two properties. Property 1, phi is continuous at A. It occurs to me I never defined continuity of a complex function for you guys. What's the definition? Maybe I did last time. I can't remember. What's the definition of complex continuity? We can state it in terms of limits, right? Limit as z goes to A if phi of z is equal to what? Phi of A, right. Just like Calculus 1, definition of continuity. Like, I thought it was something about lifting a pen. No. Incorrect. We state continuity in terms of limits. Of course, it does have something to do with that whole pen lifting thing, but whatever. So continuous means that the limit of the function is equal to the value of the function at the limit point. All right. And 2, we have that f of z minus f of A is equal to phi of z times z minus A. for all z and d. All right. So, proof. Ha, not bother me again. This direction, so how do we do it? Assume it's complex differentiable, right? Assume f prime of a is equal to the limit as z goes to a of f of z minus f of a over z minus a. That exists as a complex number, all right? Now, what do we have to do? What's our job? We need to construct this function phi. I call phi the difference quotient function because that's what it is. Construct phi of z is equal to f of z minus f of a over z minus a for z not equal to a, right? And let phi of a equals to what? I'm assuming it exists. It's within my power. I just use f prime of a, right? That's the value of phi at a. That's my construction of phi. Now what do I have to do? I need to show properties 1 and 2 hold, right? So observe, 1 and 2 hold as the limit as z goes to a of phi of z is equal to the limit as z goes to a of the difference quotient. But of course, that is what? That's f prime of a, which is by our construction, phi of a. Therefore, phi is continuous at the limit point. And how about the algebraic part of it? Number 2, it's immediate. What is number? So number 2 says what? F of z minus f of a is what? Phi of z times z minus a is true for z not equal to a by construction of phi, right? And at z equals to a, because 0 equals to 0, right? Using my little brother's word. When he was about 4, it's one of his sayings. Be like, why is that true, Andrew? Andrew be like, cuz by. Be like, okay. Andrew says cuz by, it has to be accepted. So I'm using a cuz. So there it is. Anyway, do you agree? Well, you don't have to agree. It's still true, whether or not you agree. But I hope you agree. How about the other direction of the proof? So assume phi exists, as in the theorem. Consider, the limit as z goes to a of f of z minus f of a over z minus a. Well, by 2, if you just divide z minus a on both sides, by 2, you can rewrite this as the limit of what? So that's by 2. You're like, well, you divided by z minus a. Couldn't that be 0? No, not in the limit. It can't be 0. We consider z close to a, but not a. So this identity holds for z not equal to a, which is all I need. And then by 1, by continuity, that's equal to phi of a. And so you can identify that phi of a is actually equal to f prime of a. So this is the theorem of Carathéodory. Do you guys remember how we proved things were, well, there's some things we proved in Calculus 1, right? For example, if f and g are differentiable, f plus g is differentiable, right? F times g is differentiable. F divided by g is differentiable, right? Also, we proved that differentiable implies continuous. Remember that? Let me show you how we can do that now. So here's a little theorem. If f is differentiable, complex differentiable, at z equals to a, then that implies that f is complex continuous. At z equals to a. Although, as I'll discuss in future lectures, that there is really no need to make a distinction between complex continuity and real continuity, because both the real and the complex approach use the same topology. Anyway, so how do we prove this? Proof. By Carathéodory, there exists phi, right, from D to the complexes where, A is an element of D, such that what? Phi of Z, well, more to the point, f of Z is equal to what? F of Z is equal to f of A plus phi of Z times Z minus A. See, folks, what I just wrote there is really, really why the theorem of Carathéodory is so awesome. It gives you, okay, so we work with tangent line approximations in Calculus 1 and in other places, right? This is not quite a tangent line. It's kind of like a tangent line approximation, right? But the thing is, the coefficient of the linear term, it's not a constant. It's a function. And that function has contained within it all the nastiness beyond the linear term. So it's like you've replaced the constant in a tangent line with some function. And it turns out this is a terribly useful thing. Let me show you why. So what do we have to do to show it's continuous? Calculate the limit as z goes to a, right, of f of z. What's that equal to? By Carathéodory again. But by the limit laws, this is what? This is the limit as z goes to a of f of a plus the limit. Now I'm taking out a logical loan right now. The logical loan I'm taking out is that the limits I'm writing are separately existing. If they don't, then I can't do this. But they do. So what's the limit of a constant? That's another good homework problem, or a very friendly test question, right? Prove the limit of a constant is a constant. With epsilon deltas, you can do that, right? So here's f of a. This is 0. This is f prime of a, but who cares? 0 times f prime of a is still 0. So I have f of a plus 0. In other words, I have f of a. So therefore, f continuous at z equals to a. And there you go. There's the proof that differentiable implies continuous. Now, if you think back to Calculus 1, when we asked you to prove differentiable implies continuous, it wasn't an easy thing. It involved some sort of shenanigans with limits. Those shenanigans are gone. They're replaced with this wonderful phi function, which captures in it all of the subtlety of that argument. So to prove theorems about functions with the theorem of Carathéodory, I simply take the function, replace it with its sort of pseudo-linearization, and multiply things out and collect the terms which are paired with z minus a, and that's the derivative. I'll show you next time how we can prove the product of complex functions is complex differentiable functions, complex differentiable, and the quotient, and all these things with the theorem of Carathéodory. But I don't, I do also want you to be able to go back and do Calculus 1 style difference quotients, right? That's the usual kind of standard topic. Okay, all of this said, there's one example we can't hope to touch right now, and that's this. What's the derivative with respect to z of e to the z? See, in order to calculate that, I would have to look at some difference quotient like this. And if you look at what that really means in real notation, it's quite monstrous. Because those are complex exponentials. And if you break it into a sum of real and imaginary limits in the plane, they're quite nasty. So I think if you try to do that calculation with what we currently have on hand, you probably can't do it. Next class, we'll finish up this discussion about Carathéodory's theorem, and then I'll introduce you to something called the Cauchy-Riemann equations, which give us a way of breaking complex differentiability down to the level of real partial derivatives. So anyway, with that, I think I will shut up. Aha.